Hello everyone, this is part 2 of Heapsort. Today we're going to talk about heap, how to insert a node in a heap, how to delete a node from a heap. We will also talk about how to construct a heap from an array. And lastly, we will see what is the Heapify operation. So let's first start with heap. So a heap is a complete binary tree where each node have value greater than or equal to all its descendant. So here 100 is the root node, it have value greater than its children 19 and 36. Then 19 have value greater than its children 17 and 3. Then 36 have value greater than its children 25 and 1. Then 17 have value greater than its children 2 and 7. So this is a max heap, and in a max heap root node will have the largest value. We can also have a min heap. So in a min heap, each node have value less than or equal to all its descendant. So here we have a min heap where 1 is the root node and its value is less than its children 2 and 3. Then 2 have value less than its children 17 and 19. Then 3 have value less than its children 36 and 7. Then 17 have value less than its children 25 and 100. So in a min heap, root node will have the smallest value. Now let's talk about how to insert a node in a heap. So whenever we insert a new node in a heap, we always add the new node at the last position and then move that element upwards if that element is greater than its parent. So this is our initial heap and we are going to add 75 to this heap. So we will add 75 as a right child to 44. So this is the last position in this complete binary tree. So we will add 75 as the right element of 44. Then we will compare 75 with its parent. So we will compare 75 with 44. Now 75 is greater than 44. So we will swap 44 and 75. So 75 will go up and 44 will come down. Then again we will compare 75 with its parent. Now we will compare 66 and 75. Now 66 is less than 75, so 75 should go up. So again we will swap 66 and 75. So 75 will go up and 66 will come down. Now we will compare 75 with new parent, which is 88. Now 75 is not greater than 88, so 75 will remain at its position. So this is how we add a new element to an existing heap, and then we place the element at its right position by comparing it with its parent. And if we find that the element is greater than its parent, we move that element upwards. Now let's see the array representation of this. So we added 75 at the last position, which is 11th position in the array. Then we compared 75 with its parent, so 11 by 2. So its parent will be at 5th position. So we will compare 75 with 44. Now 75 is greater than 44. So we will swap 44 and 75. So 75 will go at 5th position and 44 will come at 11th position. So in this one, 44 is at 11th position and 75 came at 5th index. Now we will compare again 75 with its parent. Now to calculate the parent of this node, we will divide the index by 2. So 5 by 2. So its parent will be 66. Now we will compare 66 with 75. Now 75 is greater than 66. So we will again swap 66 and 75. So 75 will go at index 2 and 66 will come at index 5. Now we will again compare 75 with its parent. So 2 by 2, which is 1. So we will compare 75 with 88. Now 75 is not greater than 88, so it will remain at its position. So this is how we compare element with its parent, and if we find that the element is greater than the parent, we will move that element upwards. So when we insert a new node in a heap, the element move upwards if it's greater than its parent. Now let's talk about how to create a heap. So here we have an array of 8 elements and we are asked to create a heap from that 8 elements. So first we will add 44. So 44 is a single node heap, a single node valid heap. Now next we will add 30. So we will add 30 as the left child of 44. Then we will compare 30 with 44. Now 30 is not greater than 44, so it will remain at its position. Next we will add 50. So we will add 50 at the right child of 44. Then we will compare 50 with 44. Now 50 is greater than 44, so 50 will move up and 44 will come down. So in this diagram you can see this dotted line indicates that there was a swap between nodes. So 50 will go up and 44 will come down. Now we will add the next element, which is 22. So we will add 22 as the left child of 30. Now 22 is not greater than 30, so there is no swap required. Next we will add 60. So we will add 60 as the right child of 30. Now 60 is greater than 30, so 60 will move up. Then again we will compare 60 with 50. Now 60 is greater than 50, so 60 will again move up. So this dotted line indicates the swap between elements. So 60 moved up and then again it moved up, so 50 came down. So after this is the tree. Now we will add the next element, which is 55. Now we will add 55 as the left child of 44. And then we will compare 55 with 44. Now 55 is greater than 44, so it should move up and 44 should come down. And next we will compare 55 with 60. Now 55 is not greater than 60, so it is at its correct location. Now we will add 77 to the tree or the heap. So 77 will come as the right child of 55. Then we will compare 77 with 55. Now 77 is greater than 55, so it should move up. And again when we will compare 60 with 77, 77 is greater than 60, so it should move forward and 60 should come down. So 77 will move up and 60 will come down. So this is the tree after adding the element 77. And finally we will add the last element, which is 55. So we will add 55 as the left child of 22. And then we will compare 55 with 22. Now 55 is greater than 22, so it should move up and 22 should come down. Then we will compare 55 with 50. Now 55 is greater than 50, so 50 should move down and 55 should go up. So these dotted lines indicate the swap between elements. So this is how we construct a heap. If we are given an array of elements, we can construct a heap out of those elements. Now let's talk about how to delete a node from a heap. So while deleting a node, we always delete the root node of heap, and the last node in the heap becomes the new root node. Then we will compare the root node with its children, and if it is smaller than any of its children, it is moved downwards. So while deleting a node, we move the element downwards if the root node is less than its children. So let's see an example of this. So here we have a heap and we are going to delete the node, which is the root node 88. So the last node in this heap is 44. So 44 will move up and become the root node, and 88 will be removed from this heap. Next we will compare 44 its children. So we will see the children of 44. So 75 and 77 are the children of 44. Now which one is the greater one? So 77 is greater than 75. So we will compare 44 with 77. Now 44 is less than 77. So 44 should come down and 77 should move up. So we will swap 44 and 77. So in this example we have swapped 77 and 44. Again we will compare 44 with its children. So from 55 and 75, 75 is greater than 55. So we will compare 44 with 75. Now again 44 is less than 75. So 75 should move up and 44 should come down. So again we will swap 44 and 75. So 75 will move up and 44 will come down. Now 44 does not have any children to compare with. So this is at its correct location now. So this is how we delete a node. We compare it with its children, and if we find that the children have the higher value, we move the children node upwards and the root node will move downwards. So this is how we delete a node from a heap. Now let's see the array representation of how to delete a node. So here we have the array representation. So we will delete the root node. Now 88 is the root node. So the last node in the heap will come at the root node. So 44 is the last node. So this will come at the first position and will become the root node of the heap. Then we will compare 44 with its children. So first we will see what are the children of 44. So this is at index 1. So its children are 2 and 3. So 75 and 77 are the children of 44. Now 77 is greater than 75, so we will compare 44 with 77. Now 44 is less than 77, so 77 should move upwards and 44 should go down. So we will swap 44 and 77. So 77 will come at index 1 and 44 will come at index 3. Now again we will figure out what are the children of 44. So this is at index 3. So its children will be at index 6 and index 7. Now among these two, 75 is greater. So we will compare 44 with 75. Now 75 is greater than 44. So 75 should move upwards and 44 should go downwards. So we will swap 44 and 75. So 75 will come at index 3 and 44 will go at index 7. And after that, it doesn't have any children, 44, so we don't have to compare again. So this is how we delete a node from a heap. So when we delete a node, we always delete the root node, and the last node in the heap becomes the new root node. Then we compare the new root node with its children, and if we find that the children are greater than the root node, we move the children node upwards and the root node will go downwards. So this is how we delete a node, and the last empty place that becomes when we move the last element to the root node. We can actually store the deleted element at this location. Now let's talk about Heapify operation. So what is a Heapify operation? So suppose you are given a complete binary tree and you are asked to make it a valid heap. So here we have a complete binary tree, but this is not a valid heap because 4 have value less than its children. Ideally 4, there should be an element which should be greater than its children. So this is not a valid heap. So to make a complete binary tree a valid heap, we can use the Heapify operation. So in Heapify operation, we start with the end. We start with the in the reverse order and then compare the node with its children, and if we find that the children have value greater than, we move that element upwards. So in this complete binary tree, 1, 8, 2, 3 and 9 does not have any children. So we will start with 7. So 7, we will see its children. Now its children is 1, which is less than 7, so this is okay. So we will move to element 14. Now 14 have value greater than its children, so this is also okay. Now we will move to element 10. Now 10 also have value greater than its children, so this is okay. So we will go to element 4. Now 4 does not have value greater than its children, so it means 4 should come down and a greater element should move upwards. So 14 should move upwards and 4 should come down. So here in this example, we start with 4. So we will swap 14 and 4. So 14 will become the root node of this subtree and 4 will come down. After that, we will have to again compare 4 with its children. So when we swap the element, and the element moves downwards, again we have to see with its children. Now 4 is still not the greater element than its children, so 8 should move upwards and 4 should go down. So we will again have to do a swap between 4 and 8. So we will swap 4 and 8. So we always see the children and see whether the value of the root node is greater than children. If it's not, we will swap. So we will swap again 4 and 8, and after this is a complete binary tree as well as a valid heap. So this is how we can convert a complete binary tree into a valid heap by using the Heapify operation. So in the next video we will talk about Heapsort and its implementation.